Thank you very much for introducing the workshop, QCousins, and many other stuff to our participants, and especially actively answering on questions. Not gonna lie, regularly on the workshops, we skipped such details until the end of the workshop. So now you have actually much better idea what you're getting into. So this workshop is just the very first step. For Q Germany, it is the first step to form the community, the team, that later will be also able to continue what we are doing now. And for all others, this is introduction to the quantum computing. And this is what we will actually dedicate these 4 days. And I'm happy that you all joined, and I hope that you will enjoy and will manage to learn as much as possible. I see I'm co-host, so that means I'm able to share the screen and do other stuff. And you already learned one of the main softwares that we're using. We will use Zoom for all our online meetings. So when I will give you lectures or there will be talks, and maybe something extra, all this will be mentioned in schedule as well. So I see people from time to time will appear in waiting room. Maybe I can.
I will handle them, Maxims.
Okay,
Don't
okay,
worry about it.
Okay, then I will start sharing the screen. And first I will start with the Discord. So this is actually the software where we will have asynchronous communication. So I will also stop my video just to save internet traffic. Maybe somebody will benefit from it. So you probably already noticed that we have several channels here. And by default, you were mentioned here in general channel. And we kindly asked you also, whoever is in a mood, to introduce yourself, because this is the easiest way how to get known to each other, so that you can introduce yourself and maybe you will find people who are actually living nearby and working on similar topics or have similar interests. So it is a good way to build new connections. All other channels have some functionality mostly related to the workshop events, with some maybe small exceptions. So this one is what is not available to you. It is just for us organizers to effectively communicate, maybe to improve some processes of the workshop. Here in the program will be information given to you. So mostly here we will give some announcements about, for example, upcoming events, or maybe some extra information, like if there are some difficulties that we have found how to solve. So yeah, here mostly we will announce some useful information. Here is the schedule of the workshop, and you have noticed that we mentioned which days, in which hours we are actively working. And here also we have the topics of the days. So today we'll speak about classical systems, and we'll have very small introduction to quantum programming. So very first step. And sometimes I'm joking, in the first day we already are adding something quantum, because otherwise people would say that, please give me back my money. I went to quantum workshop and still there was nothing quantum. But seriously speaking, here usually we will publish list of the notebooks that are dedicated to this day. So like today we have day 1, and these are notebooks that we will be working with. So I guess you have already received in email link for the installation with some additional installation details. I will switch the screen to show you. Shortly the materials. Those who already managed to install and launch the materials, so basically you're launching Jupyter notebooks, so like Python server, allowing us to look at Jupyter notebooks. So here is start. notebook, which is the main one that gives us access to links that lead to other materials. So basically, this is the whole course bronze that is view, and there are actually more notebooks that we will use, so there are some extras. But here you can see some notebooks have names, so 1-bit, coin flipping, and so on. And these are exactly the notebooks that I have shown you in the channel called schedule. So this is just information. What should you work with during and after the time of our meeting? And in Zoom, we have live sessions, so all links to live sessions will be published here. We tried our best to make the names of the channel self-explanatory. Here mostly will be some announcements related to the homework, maybe about the deadline or some general advices how to proceed. But the main discussion about the homework for you will happen in help channel. By the way, Pavel already mentioned that homeworks will be in Canvas, and very soon we all will receive an invitation to Canvas. And after a while, I will show you how it looks from inside. But basically here we may give some extra information about accesses and stuff. But if you need any help during the workshop, you can also ask your questions not during the workshop hours, like you can ask the next work week, and we'll still answer your questions, maybe not so fast. During the workshop hours, it will be much faster, of course, but still, whenever you have questions, you can ask them, and they are all expected in this help category, where we have, as you see, 6 channels, each of them dedicated to specific aspects. So there is programming, and we'll use Python programming language. So if you have questions specific to to Python programming, you can ask them here. If you still have issues with installation, your project is not working, then please ask your questions here. So mathematical help, if you have difficulties with some mathematical operations, need extra explanations about vectors and matrices, for example, feel free to ask questions here. This is more about quantum specific questions. Here, if you have specific questions about homework, only please don't ask for the solutions, because first of all, we will not provide you the solutions. You'll need to solve the tasks by yourselves. But maybe here you will have difficulties with understanding what actually was asked, or how we can look at such constructions or statements. So here you can discuss such things. And if you have any difficulties with Canvas, most probably related to access, then feel free to ask here. And additionally, here you can see we have 3 voice channels. So it might be the case that you started communication and then you understood that it would be good to have a voice conversation with mentor. And so here we have 3 separate voice channels. Most probably it will be enough. The next section is general channels. So here you have seen already channels general and introduce yourself. And other channels are also related to something that will happen during the workshop. You may find some typos in our material. So despite the fact that they have been improved for more than 3 years, still there is always room for improvement. So if you find typos or maybe even some suggestions, you can write here. This channel, if you would like to join the new team of Q Germany, here you can ask any questions related to how to join and basically to grow our community. Here, not today, but maybe on one of the other days, I may publish some of the quizzes that are just short questions about what we have learned so far. It is more for fun, but it's also a good way to revise the knowledge. in a very short amount of time. Here we would like to have feedback from you, so we may either post here some questionnaire or just ask you to write maybe your opinions about overall how it all went, how did we perform. And last step here, social media. Here we may post something. For example, you would like to post that you published in some social media like Twitter, your new shiny diploma after completing the workshop. Here, everyone can publish useful sources. So if somebody is interested in some topics, feel free to do it. Random, just any thoughts about non-quantum topics. So I don't know, discussing the weather, it could be, or maybe some other topics, mostly entertaining ones, but yes, non-quantum stuff can be discussed here. And coffee break is really just to chill and have some random chat with other people. And additionally, here we have voice channel for the same purpose. Let me see the chat. Overall, it is possible also to submit in GitHub. Like, I'm not sure about current structure of the access, but if your user will have access to submit the changes in GitHub, and then they can be merged into the main repository. Currently, we ask to just report typos here in some written form. Alternatively, of course, you can just change your file and maybe upload here just by giving small commentary. So if it is not possible through more automated solutions like GitHub push requests, then at least you can publish here in this channel. All right, so this is about the channels in the Discord. We highly encourage you to use these opportunities. So whenever you work with materials and have any issues or questions, just ask us here. We will have active people, mentors, and maybe me or some organizers also will help you out at some moments. But definitely ask whenever you need help. And when we manage, we will provide it to you. So that's about Discord. So now you're familiar with how it looks all on Discord and with Zoom, because in Zoom we have our meeting. And let me now shortly show you how it looks in Canvas. So when you will receive invite to Canvas, you will be able to attend our course, QBronze 91. And the main thing that you will be interested in will be these homeworks. We'll have 4 in total. You can think of each of them dedicated to the day of the workshop. So after today, you will be expected to do homework 1. And as Pavel promised, you will have 1 week. And indeed, it is so. So you are allowed to have multiple attempts. So if you submitted and got too low score, you can try once more, and you can try for multiple times. And so you can improve the grade. So don't worry if your first attempt was not lucky. You tried. If it is not good, you still can learn a bit more and try a bit later. And what is the main criteria to get diploma? So you should obtain at least 50% in each homework. So if you see here 20 points, then you should get at least 10 points. And overall score should be at least 70. So it means each at least 50, and summation should be at least 70 points from all 4 homeworks. There is 100 in total, so you should get at least 70. And just I will show you how the homework looks like. So you can take the quiz, you see number of attempts unlimited, and here you're asked some questions. So which operators are reversible? And you see here are multiple options. Some questions have only one option, and there are even questions where you need to write an answer. Usually it is very short. So yes, basically this is how your homeworks will look like. And then you will be able to submit quiz. Yes, I have 7 unanswered questions. And let's see whether I will get any points. Correct answers are hidden. And here we just state, okay, this one was incorrect. Oops. And I guess I managed to answer correctly one of the questions. I was just clicking randomly. So here we go. Here how our homeworks will look like. So this is about Canvas. So you have seen Discord, Canvas, and Zoom. And last but not least are our materials. In email, you have received a link to download. So this is where you can download materials, and either you can download as archive and then unpack it, and it will be all set. Or you can use more advanced options of GitLab. You can just clone the project. At the end, you will have collection of our notebooks available to use the whole project. So here you can see even the structure of the index of main folder. And we will be interested in start Python. By the way, if you look just at the repository, it actually renders it quite well in the browser. Okay, images are not available, but at least here you have the list of the same notebooks. They won't be running, of course, here because it is just collection of files. But if you manage to download the project and launch it as a Jupyter Notebook server, then this is what you will get, and you will be able to click the related notebooks and then do the tasks, check the information, play around with the codes. So this is the main part of our courses. This is our materials. One remark that we will not use all the notebooks, but many of them may be useful. For example, these two are to review basics of Python and math that may be needed throughout the course. So if you have some difficulties, you can definitely check those. And there will be optional notebooks also on learning materials. For example, here we have advanced. And I guess somewhere else there may be also something similar. Those are considered extra. There are some projects also available. So if you want to play around with something larger and more complicated, you can also try projects after completing the course, or maybe even earlier. There are some exercises. These are also extra. The notebooks that we will be always working with are the ones that I published in schedule. So for first day, we will work with the following notebooks. So we will work with all non-optional notebooks of basics of classical systems. We'll check the photons, so quantum coin flipping to observe unusual behavior in quantum case that is not observable in classical case. And also we'll go through Qiskit basics, so you will see the first quantum program in Qiskit. And additional extra materials about Qiskit installation and test. Maybe let me show it right now, because maybe it will save somebody time trying to install it currently. So basically this allows you to test whether your installation was successful. And let me check one more. Here in materials, there is also a file called installation PDF. So it also contains useful explanations about how to install Qiskit together with Jupyter Notebook environment. So for example, you can install Anaconda, which would allow us to launch Jupyter Notebooks. And then in Jupyter Notebooks, we can install Qiskit. And here you see Qiskit installation and test. So you can run this cell to see whether you have Qiskit installed and which version do you have. Funny enough, my is very outdated. So if I check all the notebooks before the lecture, so it might be the case that for upcoming notebook, something will not work. In such case, I will need to reinstall. So I'm just playing around also with specific case, like what would happen to the regular user if there might be some issues. So here are some commands that you may launch to install the Qiskit. So if you're able to launch all these first 3 cells and all work properly, then you have almost everything that is needed to complete the workshop. So you see here is some circuit. It was created. Then you see also drawing functionality works, MPL library, and also execution of the circuit. So launching circuits on local simulator was also working here. So we see that basically all the needed functionality has worked. Here is also complete test, and it was published not so long ago, but you see Qiskit version 37 and I have version 26. So when I launched it, everything worked last lines of the code. So if there will be something similar in one of the notebooks, then I will update my Qiskit version. Currently, I will just hope that everything will work smoothly. And this is about, in short, about the installation. So if you didn't install material still, then please use the explanations located in installation PDF file, and then please check this notebook when you manage to install Jupyter Notebook environment to work with Python. And if you manage to install Qiskit, then you're all set to complete our workshop. Let me know if you have any questions so far. Currently, it is more some technical details, organization of the workshop.
Maxent, maybe I will just announce one more thing. I just sent invitations to Canvas to the email addresses that were provided in the registration form. So I believe that all people who are invited should have received one, but if you haven't received the invitation to Canvas yet, please let me know and we'll see if there's an issue. I see there's also a question about submitting issues, PRs to the repo, like in the GitHub. So it's a question on the chat. Yeah,
I have shortly answered about that. Currently, I'm not sure whether by default we give access to registered users. So if push functionality is not working, then I currently encourage just to either share file or typos or something like that. And yes, if you have difficulties accessing Canvas, you can also approach us in this channel, Canvas Help. Let me check in announcements. Yeah, so Pavel, you also published here. Thank you. So then let's proceed with materials. Also, I will mention that the lecture time will not be the whole 4 hours. In the past, we managed 4 hours to combine both lecture part and individual work part. And we actually were experimenting with different formats. And one of them was that we first just gave students to work with notebooks by themselves, and then we gave extra explanations. In last few workshops, we mostly are first going through the materials, but maybe I will be skipping some of the details so that you will have something to work with, including the tasks. And there are some additional sources, so let's just jump into the first notebook, which called 1-bit. So we start with the very basic entity, the smallest memory unit, which is called bit. And each of the notebooks is also supplemented by video lecture. So if you need to go through it more, you might be interested also to check it. So here you can see that I guess lecture has been loaded. So you see, we also have recordings where the notebook is also followed by the lecture. So therefore, if you for some reason didn't manage to join this lecture, or you would like to check at any other time some extra information, definitely you can use this option. So we tried to build these materials so that it is possible to work with them even individually and asynchronously. So please also use this opportunity if you will need. Another thing is that mostly each notebook will consist of some information with explanations, including examples, and there will be tasks. And also we'll have some parts where the code should be input. Either it is example provided by us, or there will be some task. And also we even added solutions to the most of the tasks. So we highly encourage you to first try to do tasks by yourselves. And if you are not sure whether you solved correctly or you cannot complete it at all, then you can check the solutions as well. I will show you later how it looks like because there are no solutions. So we start with the 1 bit, and it is the smallest useful memory unit. In our daily lives, we are used to decimal number system, so we have digits like one symbol, and it can be from 0 to 9. So it is called base 10 system because we have 10 different possibilities for integer. Bit is for base 2 system. So you see there are only two options, 0 or 1. And so bit can represent some state. So state can be represented by its value. So bit can be either equal to 0 or to 1. And so then we can say that if bit value is 1, alternative way how to say it is that bit is in state 1. So we call the value of bit its state. So it might, some of the notations might be not so common for you in the past, but those notations will be used in quantum computation as well. Think of this classical part as preparation for it. So currently we look at bits as memory unit that can be in some state. And since it is the simplest one, we have just two different possibilities. It can be either in state 0 or in state 1. So many things can be described as a bit. 0 and 1 can also be interpreted as Boolean values, like 0 is false and 1 is true. And you can define many binary events in daily lives also with bit. For example, if light is on, then switch has value 1. If light is off, then switch value is 0. Currently, what is enough to understand that bit can have one of two possible states, which mostly are represented by 0 and 1. So we can have different operations on a bit. And in total, there are possible 4 different cases because we have some possibility for state 0 and some possibility for state 1. So operator will change the state of the bit. And so we have 2 initial states, and then we can have 2 different final states. So in total, we have 4 different combinations. And here, all of these 4 possibilities are described. So we have identity operator, which does not change the value of the bit. So if bit is in state 0, and we apply identity operator, then the final state will be 0. Similarly, if initial state is 1, final state will be 1. Negation changes bit to the opposite value. 0 becomes 1, 1 becomes 0. And last two operators are just constants. So for case 0, doesn't matter what was the input, output will be 0. Final state and constant 1 works similarly. So here, each of these operators is also described via text. And we can represent operators with the table. And so this is what will be important to remember. It will be needed here in classical computation, but also when we will speak about probabilistic and quantum ones. So please remember this notion. So we read our tables in the following way. On the top is state from which our bit starts, or our system later on. And here is in which state it finishes, so the final state. So from which to which state we are going. And here is identity described in the following table form. So you see columns denote initial state, so from which we start. These columns will be the final states in which we finish after applying our operator. So this table then textually tells us which transitions are performed. So for each of the initial states, we have description to which final state it is transitioned. So if we start in state 0, goes to 0. So if we started in 0, we will finish in 0. And similarly here, if we started in 1, we'll finish in 1. Let me see the chat. I'm not sure what could be the reason, because my microphone is all set. Let me see. It looks strange that sensitivity shows as if I am not too loud. I will turn a bit more. I'm sorry if this is happening. It might be internet also. Today is a specific case that I'm not at home. But thank you for informing me. So this is about the table. How we can look at our transition operators. And so here is another way how we can represent it. So now we represent all with zeros and ones. And we use 1 as for transitions that is happening. So 1 is if there is transition between two states. So from 0 we go to 0. So this is why there is entry at 1. Similarly, from 1 we go to 1. And 0 from the cases where there is no transition. So if we start in state 1, we will not go to state 0. You can think of these numbers, speaking a bit ahead, as a probabilities. So if we start in state 0, we will finish in state 0 with probability 1. Start in state 0, we will finish in state 1 with probability 0. So this is a very convenient way to use zeros and ones to show which transitions are happening and which are not. And so here is explicit explanation about these tables. And here you can see for other 3 operations. For example, for 0, you can see for both initial states 0 and 1, final state will always be 0. And so the task 1 is just to check once more. So I encourage you after the lecture to check it once more so that you understand the notation of these tables. So maybe let's check one more interesting case for not operator. So if we start in state 1, then we look at the column to realize where we go to this final state. We see 1 is here, which corresponds to state 0. So then it means that if we apply not operator to state 1, our final state will be 0. And here is some remarks. So currently we work with just one single bit. And we see that for some operators, we can easily determine the initial value by checking the final value. So, for example, if we know that final state is 0 and we have applied not operator, then it means that initial state was 1. So in case of identity operator, it's even simpler. We know that initial state was the same as the final one. For not operator, it is opposite one. But you see, it is not always the case for all operators to be able to guess what was initial state. So if we speak about operators 0 and 1, then we cannot guess what was the initial state. So if for operator 0 we have final state 0, we don't know what was the initial state. It could be 0, it could be 1. So this is one of the ways how to classify our operators. They are reversible and irreversible. So as we noticed, identity and not operators are reversible. So from final outcome, we can predict what was the initial state. So we can reverse our computation. But for operator 0 and 1, it is not possible. So they are called irreversible. This classification is important because, surprisingly, quantum evolution operators are reversible. Here is additional detail as long as the system is closed. So currently we will work only about closed systems. So you can consider that we have just fixed bits with which we are working. But this remark is important, so you can think that, okay, quantum computation allows only reversible operators, while classical allows also irreversible. So it means quantum computation bigger. Actually, quantum computation is stronger. But yeah, this is interesting remark about the fact that only reversible operators will be available as quantum evolution operators. And two for dimensional quantum operators that would work are identity and not operator. But we'll see also many others. And so this is introduction to bit. I will not stop much between the lectures, but if you have question even during the lecture, you can always write and I will react when I manage as soon as possible in most cases. In worst case, when I finish the notebook. The next one is coin flip. So we have seen single classical bit, which can be in state 0 or 1. Now let's see how we can look at probabilistic computation, and we will work with a probabilistic bit. And we start with the most widely seen probabilistic event, which is called coin flipping. So coin flipping means that you have a coin, you flip it, and with equal probabilities, it can land on heads or tails. So we can represent them with 0 and 1, and so we will have a bit. In this case, probabilistic one, because it can be either 0 or 1 with some probabilities. Usually we can consider fair coin. So fair means heads and tails have equal probabilities, 1/2, 0.5. If we want to represent this bit, so bit starts in 0 or 1, so we can consider that your coin is already with heads or tails, and then you flip it. Then it can be represented with the following operator. So if we start with heads, we can get heads or tails with probability 1/2, any of them. Similarly, if we start from tails. So as a result, we have the following table representation of our operator. So if we start with heads and we toss our coin, it will become heads with probability 1/2, and it will become tails with probability 1/2. Similarly for tails. So this is the first probabilistic operator that you see during the course. And if you write with zeros and ones, then this is how it looks. Now we would like to simulate fair coin. So this will be the task in Python, and the first case when I can show you that there are links to solutions. So when you click it, you will see here also the task followed by code solution. So you ask to think in Python how to implement the code which will imitate flipping on fair coin. Very small remark, you can use randRange function, which is already imported for this task. And so on this cell, you can write some code. For example, I would like to print random number between 0 and 1. So I will imitate a bit. So you see, it output is 1, again 1, 1. I'm getting lucky, always 1, and now it is 0. So you can write here a code that would imitate this coin flipping with help of randRange. And you would need to count how many times you have obtained heads and how many times you obtained tails. So we are simulating hundreds of coin flips. And here you asked for a specific number of repetitions. And what we should observe that results should get close to ideal case. So it will be closer and closer to be 1/2 and 1/2 of the cases being heads and tails. Probabilistic operators can also have different probabilities. So this is example for biased coin. So now we have heads with probability 60% and tails with probability 40%. And so this is the next operator that we would need to perform. So now you see we may consider having more than 2 possibilities to imitate this probability, because randRange picks random value from interval with equal probability each of them can be picked. So if we take, for example, from 10 numbers, then we can think that first 6 numbers represent heads and last 4 numbers represent tail. In this way, we can imitate probabilistic events with different probabilities. So this is what you're asked to play around with when you will work with our materials later. And you will also observe that probably results should get closer to ideal case. So since we have 60% probability of heads and 40 tails, then you see heads will be 1.5 times more frequent than tails. And what this notebook teaches us is that you see if you do some probabilistic experiments, then the more times you repeat the experiment, the closer the outcome should be to the predicted case, to the best case scenario, to ideal case. So this statistical approach may be useful, and later you will see that quantum computation also can have probabilistic outcomes, and their repetition of experiment for multiple times can be very useful. So short summary, first we have seen how we can represent regular classical transitions operators. And this is the way how we can represent probabilistic operator. Currently for a single bit. So you see where probabilities do not depend on which input we had. So it doesn't matter whether we start from 0 or 1. If our coin was biased with these probabilities, and this is the operator that will describe it. One more remark, there also exist extra parts of the notebook. So if you manage to do all the tasks and you feel bored and want to try something more challenging, then you can check also parts of the notebook that are called extra, or sometimes it is also called advanced. So here you see we have extra task, and also solutions are available. Yes. All right. This is the next notebook called game with two biased coins. This will be example of probabilistic operator where also initial state is affecting the probabilities. So interestingly, we will imitate the game with two coins. So suppose that we have some biased coin that lands on heads with probability 0.3, and it is tossed once, but we do not see the outcome. So what happens in this case? So we have seen that we have some probabilistic distributions for our probabilistic events. Like if we tossed fair coin, we will have 0 with probability 50% and 1 also with remaining probability 50%. If we have biased coin, we'll have heads in this example with probability 0.3. So even though it lands on either heads or tails, our information is probabilistic because we didn't see what it actually landed on. We know that it will be heads with probability 0.3 and tails with probability 0.7. So this is a way how we can represent some probabilistic state. So it will be 0 with probability 0.3 and 1 with probability 0.7 respectively. So in general, probabilistic bit is in states 0 and 1 with probabilities p and 1 minus p. Because summation of all probabilities should be equal to 1. So if we have 0 with probability p, then remaining probability 1 minus p, it will be in state 1. And probability is always number also between 0 and 1. So for fair coin, p was equal to 0.5. For this example, p is equal to 0.3. Remark, if p is equal to 1, then we have bit having value 1, and p equal to 0 will have bit being in state 0, so it is deterministic case. So no probabilities will be involved. So if we toss biased coin more than once, the probabilities of getting heads and tails will be the same, because we see we toss a biased coin and the outcome doesn't depend on initial state. So in following game, we will use two biased coins, and they will also have different probabilities. And the thing is that now we will decide which coin to use depending on our previous outcome. So basically this is a game. We have Ася, she has two coins. Let's call it euro and cent coin. Both coins are biased and probability are different. So for euro coin, probability of heads is 0.6. Probability of cents is for heads will be 0.3. And remaining probabilities are for tails correspondingly. So euro will have tails with probability 0.4. Cent will have tails with probability 0.7. And here is a protocol how the game is described. So Isa starts with flipping 1 euro. If after flipping the coin, whichever coin she was flipping, she gets heads, she'll flip 1 euro in the next round. If she got tails as last outcome, she will flip 1 cent in the next round. So you see, which coin will be flipped depends on the initial state. So what was the last outcome? And each coin has different probabilities. So therefore, we can describe it as an operator. Probabilities depend on initial state. So if we had heads, then we'll toss euro coin, and this column exactly describes transition probabilities for euro coin. We'll have heads with probability 0.6 and tails with probability 0.4. If we had tails, then we'll toss cent coin, and so it will be heads with probability 0.3, tails with probability 0.7. And here is our operator with zeros and ones. So we can describe heads and tails as zeros and ones. So if last coin toss we had outcome 0, we had heads, then we will toss euro coin. So this will be our probabilities to get 0 and 1. Any questions? So here you see the example when probabilities depend on the initial state. And basically this is the most general example of 1-bit probabilistic operator. Oh, thank you, glad to hear. So this is operator that describes our probabilistic operations. And here, suppose that Asa will do 3 rounds of this protocol. So we will calculate the probabilities, ideal ratio using Python. So suppose that in the beginning we have heads, because we will start by tossing euro coin. So we have probability of heads being 1, probability of tails being 0. After that, we need to calculate new probabilities. How do we calculate it? New probability of heads will be equal to, first of all, what was the probability to be in heads, multiplied by 0.6. This corresponds to the entry. So if we started from heads, the probability that euro coin will end heads is 0.6. So we multiply these two probabilities. Plus probability of being in tail. So if we started from tail, we'll have probability 0.3, so we multiply it. So this is how we obtain the final probability of heads. Even if we don't know whether we are starting with euro or cent coin, if we know the probabilities of starting with that coin, then we can describe it like this. Similarly for tails. And I will tell you now maybe a bit more threatening word. This is actually manually done vector matrix multiplication. But later we'll see also it more formally and mathematically well written. But currently here is the way how we calculate the final state from the new state. And so after calculating these probabilities, this will be the probability of having heads and tails after the first round. And then we just repeat similar calculations. So now we have new probabilities of heads and tails, and we put them in this formulae, and we get new probabilities of heads and tails. And so it is repeated 3 times, and at the end we get probability of 44% of having head after 3 coin tosses. In that you tossed your coins 3 times, at the end the coin landed, and the probability that it has landed, the last coin on heads, will be 44%. And the remaining, almost 56%, will be probability for tails. In task 2, you are asked to do some similar code, but this time you're asked to do loop to have 10 coin tosses. And next tasks ask you to repeat even more to see just how these probabilities change. And next is interesting in the sense that you start from different state. So you start not from tossing euro, but you will toss euro or cent in your first round with equal probability, or even you will toss cent coin, just to see what happens. So let me currently not explain you what you actually should obtain. I hope you will see some interesting pattern, and you may think that you did mistake in the code when you see this pattern. So if after doing all these tasks, you will think that you did mistake, please check the solutions to convince yourself. Because yes, probabilistic operators have some very interesting properties. And as I said, I currently will not tell you because you need to try by yourself. So I will not spoil the surprise. But in the next lecture, if you will have question about this, then feel free to ask me. I will gladly explain what actually was hidden here. And here additionally is extra, just trying some different probabilistic operators. So here you see, for example, game with 2 coins, where now we have general formulae where probability of heads for both of them can be arbitrary, and probability of tails, of course, is the remaining probability. So we have seen probabilistic operator in action. But what overall does it mean to have a probabilistic state? So what does it mean to have some bit or some more general system, which may consist of multiple bits, being in some specific states with some probabilities? So here we will describe it mathematically. So if I tosses her fair coin secretly, and we do not see the result, then the only information that we have is our probabilistic distribution. We know that it is heads with probability 0.5 and tails with probability 0.5, and this is it. So this is our probabilistic bit, probabilistic information that we have. If coin has bias, for example, that heads has 3 times larger probability than tails, so you see here is a ratio that head will happen 3 times while tails will happen 1 time. We can, of course, then calculate the probabilities. So we'll have heads with probability 0.75 and tails with remaining probability 0.25. Here is explanation how we get these numbers. So total probability is equal to 1. We know that we have 4 parts in total, 3 for heads and 1 for tails. So therefore, probability for any one part is 0.25. And then 3 parts are heads and 1 part is tail. So we just multiply these numbers. And so we get the probabilities. So these are 2 equivalent ways how to represent the probability. And now, mathematically widely used approach, how to represent our probabilities. We can represent them as a column, or also known column vector. So I will use drawing again. I hope one day from my drawing somebody will make NFT. So this column vector represents the 0s and 1 state probability. So now we have 2 probabilities written in column, and first entry corresponds to probability of state 0 or heads, and second entry in the column is corresponding to probability of state 1. So this is our fair coin, how it can be represented as column vector. And this is for biased coin, 0.75, 0.25. So now we have some uniform way of representing our probabilities. So these are 2 examples of 2-dimensional vectors. It is called 2-dimensional. You can think of that each number is a dimension. So 2-dimensional means that there will be 2 numbers, or probabilities for 2 different states. In our case, state 0 and state 1. This dimension, of course, can have also geometrical meaning. So if you use each of these numbers as coordinates, then you need a 2-dimensional plane to represent it. But currently, just you can think of dimension being number of these probabilities. So here is task 1. And this time I will ask you to write in the chat. So suppose that we have a coin having the following bias, that head is 1 time and tails 4 times. So tails are 4 times more frequent than heads. So we would like to represent this information as a column vector. So if he tosses the coin and we don't know the outcome, we only have this probabilistic distribution. So please write in the chat what will be the probability of heads and what will be the probability of tails. That was fast. I barely managed to ask the question. So Any other opinions? All right, I guess. Sadly, no, and let me explain why the last one is not correct. Because we have 5 parts in total. So it means we have 1 plus 4 1 part is 1 divided by 5 is 0.2, and at the end you need just to multiply number of parts by 0.2. So you have 0.2 for heads and 0.2 times 4, which is equal to 0.8 for tails. Good. This task we will not do now, but I'll just show you. So we might have also probabilistic system with more than 2 states. Here idea is tricky dice. So those who are not familiar with dice, this is dice. So you see it has 6 numbers, and with regular dice, each number can be obtained. Yes, it is correct. Thank you all. Each of the 6 sides can be of equal probability. In this example, this dice is tricky, so biased. So each part has different probability. So we see we get number 1, state 1, let's say, for this dice, with 7 parts, but we get state 6 only with 1 part. So we have this proportion of probabilities of getting one of 6 states, and we would like to represent it as a column vector. So we should do something similar what we did in task 1, but this time with 6 states. And this will be task 2. Now what I want to show you is vector representation. So suppose that we have system with 4 distinguishable states, S1, S2, S3, S4. So we represent them as 4 numbers, and we can think that our system is in one of the states with probability 1. So you see, deterministic states can be represented as probabilistic vector, where entry has value 1. So we have 4 different states, and we denote that here. Let me use like 1, 2, 3, and 4. So we state like which state it is. We see that 4th state is represented a state where entry in this example, we have that state 1 is having state 1 with probability 1 and all other states with probability 0. So this is how the deterministic states look like if we represent them as column vector. So it allows to represent informational system where we have also more than one state with some certain probabilities. So now suppose that we have all these states with, I thought I pressed clear. Yeah, I need to click sometimes several buttons just to remove it. So suppose that we have the following column vector. It states that we have state 1 with probability 0.2, state 2 with probability 0.25, and so on. How do we represent it? We can actually represent it like this. So it is 0.2 of state 1 plus 0.25 probability of state 2, and so on. I have written down these columns separately. The remark is, of course, the total probability should always be equal to 1 to have well-defined probabilistic system. But yes, here is the representation, how we written it explicitly, that we have states 1, 2, 3, and 4 with these probabilities. And this is what we can do next. So basically, this states that we have first state with probability 0.2. We have second state with probability 0.25. So we write down all of them explicitly. And we just sum all vectors together, and this is the final vector that we get. So we have 0.2 probability of state 1, 0.25 of state 2, and so on. So now you see the explicit way how to look at column vectors. So if you see something like this, it means exactly that is stated in this line or this line as well. So it is just 0.2 probability of state 1 and 0.25 probability of state 2 and so on. So we have pluses. And this is summary of probabilistic states. And here we speak that it is in standard basis. Currently, you can think of standard basis as being just bits basis states, zeros and ones. Or it can be just numbers from 1 to n, where we have n elements. Overall, probabilistic state is represented as a vector, column vector. Each coefficient should be non-negative, and summation of coefficients should be equal to 1. Probabilistic state is probability distribution over the deterministic states. This is what we have seen here. We have probabilistic distribution over deterministic states. And what is beautiful mathematical solution is that it can be represented as a single object. So stochastic vector is representing our probabilistic state. And this is how our stochastic vector looks like. So system can be in such probabilistic state. Here will be more challenging Python task where you need to randomly create a probabilistic state. So you would need to pick 4 random numbers, and then you need to normalize, because you should always ensure these properties. Summations of coefficients is equal to 1. Because for well-defined probabilistic system, summation of probabilities should be equal to 1, which means that if you did some probabilistic experiment, one outcome should definitely happen. And here is extra task, which is advanced version of task 3. I'll just shortly check the Discord as well. Okay, so there is activity only in introduce yourself and in slides. Okay, so we have 2 more notebooks about probabilistic systems. So we were speaking about probabilistic state. So we have seen it is column. Where some all elements are non-negative numbers, and summation of all these numbers should be equal to 1. Now about probabilistic operators, so our tables. This was of our ICES coin flipping game. So remember, here we had heads and tails with some probabilities. We start from heads or tails, and we have then probability to transition to heads and tails. So now we try to describe also the process with help of our vectors. We start in state 0. So we start with head, so we will flip euro coin. And we can represent our state in this way. So we have 0 with probability 1. This is a vector that represents it. State 0 represents heads. And then we do the coin flip. And here we see vector matrix multiplication in action, which was manually computed, as I have shown you, in our coin flip game 2 notebooks ago. Here now we write it explicitly, that here we have our current state, and we apply to it our operator. So it is vector matrix multiplication, and you see we use a convention that we multiply by matrix on the left side. It is a convention that is also used in quantum computation, so please get used to such vector matrix multiplication. Interestingly, new people are still coming. That is good. So here is our calculation. So we have we multiply this vector by this table, by this matrix. So we'll multiply 0.6 by 1, probability of heads from heads, plus 0.80, which means probability to get heads from tail. And we'll sum these two numbers together. Similarly, we compute probabilities to get to the tails, and we write them now explicitly, these summations. And so we get, at the end, probability of heads 0.6 and probability of tails 0.4. Then we apply second time this operator. So we do the second coin flip. So we just check, get our state from previous calculation, and we again apply our operator. So here calculation is a bit more interesting because we don't have zeros. And we'll get 0.48 probability for state 0, 0.52 for state 1. And so this we start with some state. We apply coin flipping protocol, which is our operator, and we get new state. Apply it once more, and we get new state. So if we would start from this state, we would get this one. So when we calculate the new state, we use this game coins protocol, which is represented by this matrix, to the current state. So this is example to state 0802. We'll get this state 0.54, 0.46. What can we tell about probabilistic operators? So first of all, each entry should be non-negative because, again, all entries are representing probabilities. Each column represents transition probabilities from state to all states. So summation also should be equal to 1. Therefore, for each column, summation of all entries should be equal to 1. And you can see it here. 0.6 plus 0.4 is 1. 0.3 plus 0.7 is also equal to 1. So this probabilistic operator is represented by matrix, and it is also called stochastic matrix. So probabilistic operator is a stochastic matrix. And here, just summary of probabilistic evolution. So we have our probabilistic state stochastic vector, and we have probabilistic operator. So when operator is applied to our state, new state can be calculated as vector matrix multiplication in this way. And more correctly, say matrix vector multiplication, because we see on the left side we have first matrix and then we have vector. So if it is our matrix, our probabilistic operator, and we have probabilistic state this one, then by performing this probabilistic operator to this probabilistic state, we get new probabilistic states, this one. In task 1, you would need to verify it. And task 2 asks you to just to check whether you remembered quite well how to read probabilistic operators. So I ask you to write in the chat answer to the first question. What is the transition probability from the second state to the third state? So please write your answer in the chat. So one of the answers is 0.3. Okay, one more 0.3. So you remember my explanation that we read matrices in this way, from which state to which state we're going. So we go from state 0, from state 1, from state 2 or state 3, first, second, and third, to first, second, and third state as well. And so the question here was from second to third. And this is from second to third. So probability 0.3. So your answer was correct. let's this time answer somebody else. I will ask last question. What is probability from first state to second state? So please somebody answer this question. 0.2, okay. 4 answers. 5, thank you. So from first state to second state, exactly this one. So now by knowing this trick, you will be less afraid of matrices if you were before. So this is the way how we can read matrices. It just shows, in case of probabilistic computation, probabilities of transition from one state to another. And this is how we read it. Nice. Thank you. And last tasks here are related to programming this. So in task 3, you would need to construct randomly probabilistic operator. So you will need to ensure it's a related topic. So those who are curious, so it can be expressed like in several ways. But it's indeed very related to transition of probabilities between some states. Currently, we have just one operator. We may also consider multiple operators. So yes, here the task will be to construct probabilistic operator. So you would need to ensure that summation of probabilities in each column is equal to 1. Here you would need to do matrix vector multiplication by hands. So this task will require a bit of effort, but at least if you manage to program this, then you can be pretty sure that you feel confident in how to multiply vectors and matrices. And then you can just use this code. And here you would need just to experiment by applying matrix multiplication for multiple times and see how it evolves. So yeah, these are mathematically intenser tasks. This will take you more time than all previous ones. But please try to do them. It's also good practice in programming as well, to manipulate with arrays of numbers. So this is the last notebook of probabilistic systems that we cover. I have mentioned that there are more advanced ones, and so you can check them, and even you can ask questions about them on Discord if you want. But this is what we will not cover in our general meeting. So yeah, I encourage those of you who want to check extra materials that you indeed can do it and ask your potential questions in Discord. It sounded windy there. Okay. Yes, matrix multiplications can be done more efficiently than just like how we are expected to program it in these tasks. So yes, definitely there are possibilities to do it more efficiently. There exist solutions that don't require cubic time complexity, for example, I have heard. But yeah, this is just straightforward way how to do it. All right, the next topic is two probabilistic bits, the last probabilistic topic. So basically, how can now system of 2 bits together? This general idea will be useful also later on in quantum computation, how to transition from one to multiple bits. So suppose that we have two probabilistic bits, and they have the following states. So first one is in state 0 with probability 0.2, in state 1 with probability 0.8. The second one is in state 0 of probability 0.6, in state 1 with probability 0.4. What is the state of combined system? So we need to analyze the probabilities. So new system will be in 4 different states, because when we have 2 bits, we have 4 different combinations. We have 0, 0, 0, 1, 1, 0, and 1, 1. So what we see here. And so 0, 0 represents when both bits are in state 0. And for example, 1, 0 means that first bit is in state 1 and second is in state 0. So my question to you, what is the probability of 0, 0? If we have one bit in this state, second bit in this state, and now we want to have both of them in state 0. So one answer is 0.12. All right. So you probably have guessed that this number, well, it depends. But in this exact example, we have state 0 in first bit with probability 0.2, in second bit with probability 0.6. The probability that both events happen simultaneously is equal to multiplication of these probabilities. Yes, this case is not when they are mutually exclusive. We are interested, like all 4 possibilities are available and these 2 bits are independent currently. So this was the answer, but yes, it is interesting that you also consider whether they are mutually exclusive. Currently, we consider that both these probabilistic events are independent. This is why we state first bit is already with these probabilities and second with this. And now we just combine the system. So yeah, what are the probabilities of all these states? And here is another way how we can represent our states and how we can write the composite system. So basically we tensor them together and probabilities will be multiplied and states will be written close to each other, like 1 tensored with 0. So I will show you now from the solutions. So basically, you can either do it explicitly here by multiplying each entry separately when you want to show the state and probabilities of combined system. So you see it is 0.12 probability of state 0, 0, for example, and remaining 3 states. And another way how to do it is just by tensoring both vectors. And final vector will be equal to first value. So you see it corresponds to state 0, 0, and 0, 1. So we have 0.2 multiplied by values of this second vector, and we obtain these 2 probabilities. And similarly, we calculate the remaining 2. And this is if you look at basis states, how they're tensored together. So now it makes a bit more sense why these 4 states represent 0, 0, 0, 1, 1, 0, and 1, 1. So this is how it looks when we have more bits. So this is when we got 2 bits. And it is possible also to extend it, for example, to 3 or 4 bits and so on. So this tensoring operation will be useful. So tensoring in general is how to write 2 systems as combined one system. So let me know if you have any questions. All right, so I'll see. Okay, thank you. Thank you. I will also emphasize on the fact that still we're going through materials in a bit increased speed, meaning that we are skipping the tasks. Because we work asynchronously, then you can do them at any moment, and also potential questions can be discussed. I recommend you to go through once more, because first of all, you need to experiment with the tasks, and secondly, it allows to revise everything. But yes, if you would need, you can also watch the lectures. Basically, you can think of just going through notebooks supported by lecturer voice. Now we will speak of something different this time. So you can also see that we have sections. This time is photons. It is just to show you some surprising property of quantum computation. So previous notebooks were more mathematically heavy. This one can be considered more entertaining. So we will explain series of experiments and try to understand basic behaviors of particles. We will speak about the photons. So we'll trace behavior of a photon, and we will imitate coin flipping, this time in quantum setting. So for quantum coin flipping, we will use beam splitter. And we will use also two photon detectors. So we can think of photon is representing our coin. Then beam splitter is what flipping the photon. So it will be like coin flipping. And photons then can go through beam splitter in one or another direction. So this will represent our probabilities. And then photon detectors can be our eyes. So whether we see this photon light. So this is how experiment is set up. We send photons to a beam splitter as shown below. So we have photon source and goes through beam splitter, and it can be transmitted, so it goes through, or it can be reflected, so it goes up in this example. So beam splitter either transmits or reflects the photon, and we design it in a way that probabilities are equal. So it is possible to polarize beam splitter so that it will pass photons through or reflect them with equal probability. So here is also interactive tool called Quantum Game. I guess it still all works, yes. So you can also play around with experiments here. And not gonna lie, I didn't check it for a very long time. But it is possible to play around here with imitating also photons, beam splitters. Yeah, so I won't be able to do it in one sitting currently, but you definitely can play around with it. Or maybe this one. Yeah. So you see, this is our photon and this is our beam splitter. So this is just a regular mirror. And now let's see, this is a beam splitter. So you see, it will go through with 50% probability it goes straight, and with remaining 50% probability it goes up. So photon beam is split. And so this is experimental results. So researchers have made this real experiment, and this is what has been observed. So if we interpret this as a probabilistic state, we can think of beam splitter behaving similarly to fair coin. State 0 will be transmitted, so heads will represent state 0 transmitted. tails state 1 will be representing reflected state. And so here we model our experiment as probabilistic bit. We start in state 0, and with half probability it will be in state 0, with half probability it will be in state 1. The second experiment now, we will do two coin flips in the following way. So you see, if our photon has been transmitted at first, it will go through beam splitter again. But if it has been reflected, it will be on detector A. So if we think about it probabilistically, then we can think that with 50% probability it gets stuck in state 1, with 50% probability it goes to state 0, and then it gets through the second beam splitter with equal probabilities. This is how we get probability 0.5 and 0.25. So this is our prediction. And experimental results also were the same. So photon source in state 0, we end in state 1 with 50% probability, or we go through the second beam splitter, and so we have 25% probabilities for remaining two cases. Now the last third experiment. So now suppose that we pass each time photon through both beam splitters. So if it has been reflected, it will still go through the same beam splitter. If it has been transmitted, it will also go through the second beam splitter. So we have now only two detectors. We removed detector A. We only have B1 and B2. Our prediction is, of course, that we have probability 50-50 because we'll have some probabilistic state, but we apply again the coin flipping. So if we do it by matrix vector multiplication, this is how it will be. So we start in state 1, 0. We multiply it by this matrix, and the result will be equal to the first column. So we have 1/2, 1/2. If we start from state 1/2, so second step, and apply this operator, we'll get again state 1/2, 1/2. So this is our prediction. So we predict that we will be on both detectors with equal probability 50%. However, when real experiment has been done with photons and beam splitters, this was the outcome. So you see quantum particles behave not like probabilistic ones. We started from state 0, and doesn't matter whether initially it has been reflected or transmitted, at the end it's still all finished in state 0 with 100% probability. So only detector B1 has absorbed photons. So we may conclude that classical Newtonian mechanics that were explaining our probabilities fails to explain the behavior of particles. So there's something different is happening. And we will need new mathematical model. And so we will be able to explain our experiments by using quantum mechanics. So you can think of that our photon has some kind of memory. This is false explanation. So this is just the idea like what is different here. You can see that if it reflected here, it will also get reflected here. But if it transmitted here, it will also transmit here. So these are the only two ways how we get here. So it looks as if photon would have some kind of memory. The situation is a bit different, but this is just like naive way how to think about it. So there happens something more under the surface that is behaving differently from probabilistic expectations. So somehow if we started from state 0, we'll always end in state 0. And tomorrow we'll play around with the codes that imitate these situations. So this was an entertaining lecture. We'll have now final notebook for today. I'll just shortly check. Okay, in Discord there started to appear questions in homework help and Python help. All right, nice. I see also people are answering the questions. So let's then focus on final notebook. So we have seen Qiskit installation and test already. So those who struggle with installation, please proceed with it after the lecture. But here we have first quantum programs with Qiskit. And this is final notebook, but it is not so short. Every reversible classical program is a quantum program. So we start with something that we do classically, but we will use now quantum circuit. And we will first start with not operator because we remember that it is a reversible one. And so for our quantum programs, we'll design quantum circuits by using framework Qiskit. And we start with just single bit. Quantum bits are called qubits. And later we will see a lot more explanations about qubits tomorrow. Currently, just think of qubit just representing a quantum bit. So here are codes with commentaries. So I go shallowly through it. So we design quantum circuit with single quantum bit and single classical bit. We'll apply not operator on the quantum bit. Then we measure the quantum bit and outcome of it will be saved on a classical bit. So we have quantum information, but in order to get some bits as answer, as output, we need to get classical information. This is why we use classical bits as well. So mostly we will design quantum circuits that both have quantum and classical bits. We will do quantum computation on quantum bits. On classical bits, we will get our answers. So here we are. We first import necessary libraries to create a circuit. Zoom states that my internet connection is unstable. I hope it won't be so terrible. So first, we create a quantum register. We can provide even a name to it, but what is important, we have one quantum bit. And we have classical register with one classical bit. And then we define a quantum circuit that will have both this quantum and classical bits. After that, we can apply some operations to quantum bits. Keep in mind, initially, all qubits or quantum bits are in state 0. So now we apply with this syntax operator X, which is representing not operation, on qubit 0. After that, we do measurement, and this states that we take qubit 0 and store it in classical bit 0. So currently, answering your question in the chat about why we can't implement a reversible gate, basically, if we have closed quantum system, as stated in first notebook, we can only perform reversible operations. So it is like you still should keep all particles available to us. So like they can have their states changed, but all operations behave in a way that we can reverse them and return to initial state of the system. Irreversible computation can be made reversible, but you may need additional bits or qubits. So currently, just assume that since we work just with fixed quantum space, with our quantum bits, we only are able to use reversible operations. Later, we will see that there is a reversible operation. I will speak more about it in next lecture, which is measurement, because measurement is losing extra quantum information. Yes. So you have a quantum system. It has some state, but you cannot know until you do the measurement if you did some operations, because quantum system can be in superposition. We will speak more about this in tomorrow notebooks as well. Currently, what I can tell you, it is possible to initialize the system in specific quantum state. So quantum computers usually are designed in a way that initial state of a qubit is 0. So this is why here we have applying our operation to qubit, but we know that when we created quantum register, our qubit is in state 0. It is possible to visualize the circuit, and mostly we will use matplotlib library, which is done just in this way. So this is our circuit. So we have quantum register on top. We have single qubit. We apply X gate to it, our NOT operator, and then we do measurement and store in B. So there is also convention how quantum states are represented. So this is how state 0 represents, and state 1 similarly with cat brackets. So currently you can think just that these brackets are used to denote exactly quantum states. In general, it also has mathematical meaning. Currently, just consider this as convention. So we have wires representing our qubits. So you see circuit looks like a digital logical circuit. So we have some quantum bit, we apply to it operations, and we do measurement at the end. Now we need to execute the circuit. And we will use it on local simulator. So this code is not running on special quantum computer, it's actually being simulated on your computer. And number of shots is how many times the computation has been repeated. In this case, it was repeated 1024 times. Why we may need more shots? Because outcomes of quantum computation can be also probabilistic. So this is to get at least some statistics of our outcomes. Here, since we start in state 0, as I said, initially all states are 0, and we applied NOT operator, then at the end we have state 1 in all cases. So with probability 100%, so 1024 times out of 1024. And it is possible to plot the outcome as well. And this is extra, which we will not use, but there also exists quantum assembly language, so it is possible to translate it. You see it's still quite similar. We have quantum classical register, we apply X gate to quantum register, and we do measurement. So it is possible, of course, to have more than one quantum bit. In this example, we have 4 quantum bits. And then we apply NOT operator to each of the quantum bits different number of times. So we can draw the circuit and it looks like this. Keep in mind that when we draw the circuit, default order of quantum bits will be from 0 to 3. So like from smallest to biggest index. And it is possible to reverse the order. It will look like this. So see 3, 2, 1, 0. So you see it's like mirror from this. And it may be important because the question to you, so if we would launch this circuit, what will be the outcome? So guess what will be the result? What we will have on 3, 2, 1, and 0 on each of the qubits. So please write in the chat what will be the values of our quantum bits at the measurement. So the proposal is 1100. Okay, so you see we applied NOT operator to first one only one time, so 0 became 1. If we apply 2 times in a row, we again return to 0. So in second case also we get to state 1. And in last 2, we have pair number of NOT operator. So we will get back to the state 0. Very good. So we compare our result with the called outcome, and indeed we obtained in all 100 cases 1100. You have seen here, we go from 3 to 10, and we exactly obtained what we have predicted. So order in Qiskit is the following one. This is what I will remind you in upcoming lectures again, because it is something that is very confusing to people in most cases. So you see, this is the convention of how Qiskit is giving the order of qubits. So when you see output 1100, you know that it's from largest index to smallest one. So it is called also big endian, if I recall correctly. And it has actually one of the reasons why it did so, because we can represent in such way binary number. So you see 1101 is like 1 multiplied by 2 to the power of 3, which is exactly corresponding to quantum register 3. Quantum register 0 will store the value of bit 2 to the power of 0. In this example, we have 1101, so quite similar. Here is speaking a random number in Python. So some things that actually we had already in notebook number 2. Historically, it happened that this notebook actually was usually considered as the second notebook. But now we are considering it only after finishing the classical part. So historically, this was the first place when rand range appeared. This is why here it's written so in so details. But now you can see how rand range works. So if we launch it again, different random numbers will be generated. So you see rand range n means number between 0 and n minus 1. So you can get 19 and you can get 0 as well, and any number between them. So here is the task. This will take some time, but it's again about quantum circuits and applying X-gate that we have seen so far. We need now 8 quantum bits and 8 classical bits. So you can consider this example where we had 4, but now you would need 8. For each quantum bit, you will need to flip a coin by Python. So you would need to use rand range. And with 50% probability, for example, you will apply X-gate to specific qubit. So for each quantum bit, you may need a loop. Then you will apply X-gate if with 50% probability if outcome is heads. At the end, you will need to do measurement, and you need to execute circuit 10 times. Execute circuit 10 times means number of shots should be 10. And you can repeat this task as much as you want and enjoy random choices. Means that if you repeat this task again, then different circuit will be implemented because of this probabilistic aspect. So this is just playing around with probabilities by designing quantum circuit. But keep in mind, what is the workflow here? So you have written classical code that has quantum operations. Then you do probabilistic experiment, and based on it, your quantum circuit will be formed, something like this, for example. And after that, so it is created, it is fixed, and then you do the shots. This is why you will not get different outcomes here. You will get always the same outcome for all the shots. But if you launch the experiment again, your coin flip outcomes may be different. So yeah, some difference between shots and these probabilistic experiments. If you will be misled with this task, feel free to write in the chats of Discord. We'll be happy, because this might be one of the most misleading parts. So basically, this covers all the notebooks that were planned for today. So we covered the probabilistic systems. We had fun with quantum coin flipping. And we checked these 2 notebooks. Tomorrow, we will work with notebooks related to a single qubit. So all these ones, except exercises. It will be published later in schedule. So workshop times that are related to lecture times is they are still the times when we can help you very actively. So first of all, before I finish this session, you can ask any questions, either here in the chat or with voice. And after that, I will finalize the lecture, and then you can continue working with notebooks by your own. And I remind you also that today we have let me say just in case. So today we will also have a meeting. So Zeki, maybe you can just remind for participants, it will be at 16, right? 18.
Yeah, it will be basically in 1.5 hours. And Arthur and I will talk about, Q Germany, the formation and the meeting on how to join our efforts, and to basically a little bit more on Q World and our mission.
All right. Will participant use different link?
I will share a different link on the Discord channel, and I will tag everyone so that everyone gets a notification. And it will be a kind of an informal / partially formal session that we can chat and people can ask questions, and we can further elaborate on why we are doing this.
Okay. We can then publish, I guess. Okay, if you will announce this link later, I think everyone will notice. I will just write in the schedule as well.
Yeah, and maybe I can also note that today's session is also recorded, and I will download it, edit it, and re-upload it, and again tag everyone and inform you that basically where you can reach this recording. It won't be public. It will only be available to you. So it won't be on YouTube. So please let me know if you have access issues when I upload it. But it is for tomorrow. So, and also please don't hesitate to write me on Discord.
Yes, feel free to write to any of us. One more remark: if you have more general questions, then better to write them in the threads in the channels, so that you have higher probability that somebody will notice it faster. If you write personal messages, there might be a bit bigger delay.
And maybe I can also comment that when you have questions for mentors, in the channel, it may also help to tag like @mentor, so that the mentor can see they get a notification. We are looking at the channels, but I assume that if it's an urgent thing, it would be better to have a notification.
All right. Thank you, Zeki. Chat. We're using a classical pseudonumber generator. Yes, it is pseudonumber generator that has been used. So you generated random bit, which was used to decide whether to apply operator to a quantum register. This, as I said, is one of the trickiest parts actually in this notebook. Quantum register is always initialized in state 0. All right. If there will be more questions, feel free to contact us on Discord. And one more thing before I conclude this lecture. Tomorrow we'll continue at the same time, but also keep in mind that it is always possible to ask any questions of previous lectures as well. So if after some time you will understand that you would like to discuss something about today, we still can do it. Yes, now you're free to work by yourself with notebooks and ask any possible questions in the process on Discord. And at 6 o'clock, then there will be informal meeting.
Yeah, thanks, Maxim. And one very quick, not announcement, but clarification. In the schedule, every time is giving it, UTC plus 2 or CEST plus, no, just CEST. But we realized that in the evening of 29th, there will be the time shift, yeah. So just assume all times are given in accordance to Berlin, okay? Regardless of it is CET or CEST, so I don't want to, yeah. It is 6 p.m. in Germany.
But it is meeting for everyone.
Yeah, of course. Everyone is welcome to join. I just want to clarify for the, to the 29th and the 30th that there might be a confusion regarding time zones and time differences, but it will be the same hour. We are not going to shift it.
And also, I will do my best to again remind on Saturday, next Saturday, about time shift. I guess we'll also publish it pretty soon in announcements or schedule, so let's inform as many people as possible.
Yeah, of course, but I just want to give people a heads up because it might be a little bit confusing. It was confusing for us as well, so we didn't consider the time shift while scheduling the program.
I'm also not 100% sure still if it will work well in Canvas, so we can give just extra 1 hour.
I will share the link. So I saw in the chat that somebody is asking regarding today's meeting. I will share a link. So I guess people are free now, Maxim?
Yes.
Okay, thank you. So
yeah, thank you too.
Should I conclude the meeting?
Yes, I think so. People already started to say bye. Then
Okay.
we will meet tomorrow at the same time. So at 14 o'clock, we'll continue with our quantum journey. We just barely scratched it. Tomorrow will be fun. Have a nice evening and good luck with tasks.
Thanks, Maxim, and thanks everyone for joining today.